Lesson 22 is about graphing rational functions. So 22.1 will just introduce some key features of them. We're going to start on the left side of the page with asymptotes. So asymptotes are lines, they're kind of like imaginary lines that the rational function will approach but never cross. So there can be horizontal and vertical asymptotes. If we look at the graph right here, um, there's like those two red dotted lines. Those are not actually like technically part of the graph. They're drawn into it to kind of see what the asymptotes are. But if like you were graphing or if you were to take the function and put it in a graphing calculator, these two like red dotted lines would not actually pop up on there. They're just to kind of see that the actual function, like the purple curved lines, will kind of approach them, but they never actually cross them or touch them. And I've noticed like in a lot of the workbook pictures, it does kind of start to look like the line does like cross over the asymptote or the dotted line. However, but just picture it as if it's getting infinitely close, like closer and closer and closer, but never actually like touching it or crossing it. So they're like these imaginary boundary lines of rational functions. So it's a good kind of point to review what the like equations are for writing vertical lines and writing horizontal lines. So if we look at the vertical asymptote, it's a like line that goes up and down and it crosses through the x-axis at -4. So that means that that vertical line, the equation for it would be x equals -4. So every vertical line is always x equals, and then it's whatever number it crosses the x-axis at. And then for the horizontal asymptote, you can see it's like on the x-axis. A horizontal asymptote is always y equals, and then it's whatever y value it crosses through. This one's a little bit kind of funkier to look at because it's exactly on the x-axis, but if it's exactly on the x-axis, then it's crossing through at y equals 0. Okay, so biggest thing to know is that for vertical lines, they're x equals, and then horizontal lines are y equals. So you'll be asked to, in some cases, like write the equation of a horizontal asymptote or write the equation of a vertical asymptote, and you would want to know that horizontal is y equals, vertical is x equals. Okay, so those are asymptotes. They're just, like I said, imaginary boundary lines that the graphs of rational functions will like get infinitely closer to but never cross or touch. Some rational functions also have something called holes, which are kind of exactly what they sound like. So on the right side of the page, holes occur when the function gets infinitely closer and closer to a point, but never actually touches the point. So if we look at this graph, there's a hole in the graph at -2, 1/2 right here. So it's kind of like instead of like with asymptotes, you have lines that are boundary lines that your graph will never cross or touch. A hole is more of just like kind of a specific point that your graph will never touch. And it'll just kind of like go through it, but like there will be a gap there, essentially a hole. So it's like it's named really well, at least I feel like. So on this graph, like I said, there's a hole right here at -2, 1/2. And we'll get into like what causes those later on in the notes as well. It's just kind of important to know that they do exist for now. Okay, so holes and asymptotes, those exist with rational functions. That's basically just because there's certain things that make rational functions undefined because rational functions are like fractions. So for example, like you can't have a 0 in the denominator of a fraction. So that would definitely mess up a graph. Okay, so moving down to domain and range. For domain and range of rational functions, because these functions have holes, figuring out the domain and range is a little bit trickier than we've done so far this year. Just covering them up for now because they're a little bit much to take in. I just want to talk about it conceptually for a little bit. So for the domain, if we have a vertical asymptote, that impacts the domain because if we picture like this graph, for example, has two vertical asymptotes, it's kind of separating the like possible x values into like different groups on the graph. So we have a vertical asymptote right here, because you can see like the function itself kind of shoots up along that line and shoots down along that line, but it's never crossing that line. And then there's another one right here, because of that same trend is happening. You see like the graph is shooting up along that line and down along that line, but it's not actually like crossing that line. So just as a way of practicing, we'll figure out what the equations are for those asymptotes. So for the one on the left, it's a vertical asymptote, so it's going to be x equals. And then the like x value that it crosses through is at 0. So it's x equals 0 for that one. And then for the one on the right, it's a vertical asymptote again, so it's x equals, and then it's crossing through x equals 4. So that would be x equals 4 for the second asymptote. Okay, so our vertical asymptotes, they're basically like separating the graph into thirds. So you can see like there's this third right here. There's this third right here. Not like even thirds, sorry, but like 3 different sections, I guess would be the better way to say it. And all of those sections are representing like different possible x values. Like there are all the x values that are to the left of x equals 0. There's all the x values that are between x equals 0 and x equals 4. And then there's all the ones that are to the right of x equals 4. So they're like kind of describing like different possible x values that we have. So since there are 3 different sections here, we're going to have at least 3 different sections in our domain, 3 different intervals in our domain. There could be more depending on the holes in the function, which this function does have a hole, so we'll have to keep that in mind. And then for horizontal asymptotes, so I'm going to leave that there. For horizontal asymptotes, they impact the range of the graph. So this graph just has one horizontal asymptote. We'll draw that in right here. And then horizontal asymptotes are always y equals, and then whatever y value they cross through on the y-axis, which it's at like y equals 0, or it's exactly on the x-axis, so it'd be y equals 0. And then that horizontal asymptote, it cuts the graph kind of like in half, but like up and down instead of left and right. So there's like this top portion, everything that's above that horizontal asymptote, and then there's this bottom portion, everything that's below the horizontal asymptote. So in that case, there's going to be like at least 2 different sections, 2 different intervals that we have to describe for this. So we just kind of got to keep that in mind. It's going to be a little bit like longer of a process to define domain and range because there's all those different sections. Okay, and then I kind of mentioned this before, but a hole is going to impact domain and range because it's like I said, it's just a hole in its graph. We can't touch it. And if it's a hole, like it's an exact point. So like that is a point, like an x coordinate and a y coordinate, an x coordinate that can't be a part of the domain, and a y coordinate that can't be a part of the range. So it impacts both there. Okay, so I'm just going to uncover the domain now and we'll talk through each part. There is an example we're going to do where we kind of do it from scratch, but I think this one's kind of nice just to take it in for a second because it is a little bit longer. So the domain, this is the interval from negative infinity to negative 3. And then this little kind of like U type of symbol means union. So it's just like connecting all of these possible intervals. So negative infinity to negative 3. So that's saying everything to the left of like this point. Because that point is at x equals negative 3. And then exactly at that point, there's a hole. And then after that point, we can go from the point to that asymptote, which is x equals 0. So the next one is negative 3 to 0. And remember, domain, like the boundary lines, should be your x values. So negative infinity to negative 3, excuse me, means up until that negative 3x value. And then for the second interval, negative 3 to 0 is from that point, x equals negative 3 to x equals 0, the first asymptote. And then next we can describe the space in between those 2 vertical asymptotes, which is between x equals 0 and x equals 4, So from 0 to 4. And then we have this section that's everywhere on the right of that last vertical asymptote. There's no holes on that side, so we can just say from x equals 4, that last the last vertical asymptote, to infinity, so everywhere to the right of it. Okay, so we had 3 sections based on like the asymptotes, but the hole kind of puts another spot in that we have to put a boundary. So there's everywhere to the left of the hole, that's the first one. Well, let me switch all these back to not dotted lines. We have the first one everywhere to the left of the hole. We have from the hole to the first the first vertical asymptote x equals 0. Between the 2 vertical asymptotes, and then from the last vertical asymptote and then to the right. Okay, and then like I said, that little u, I'm going to add it written in as well. It just stands for union. So it's kind of like connecting each of those intervals. Okay, so that is for domain. For the range is impacted by the horizontal asymptote, and then also if there's a hole that impacts the range as well. Remember, you'll see the hole in both the domain and the range because of like it has an x and a y coordinate, so it falls under both categories. So first from the asymptote though, the horizontal asymptote kind of breaks it into like the top half of the graph and the bottom half of the graph. So there's that bottom part, and then there's the top part up here. And then that hole is kind of not in the middle. I mean, the asymptote's in the middle, but the hole is kind of within that top part, but towards the bottom. Okay, so for our range now. So we always want to start with kind of this like lower part of our range. So we know we're definitely going down to negative infinity. That's everything that's like below the horizontal asymptote essentially, because we have no holes down there or no other horizontal asymptotes or anything like that. So one point that got kind of added in, this won't necessarily always be there, but because it's there, we want to include it, is this point 2, negative 1/4. And you can see it's really tiny, but it's, sorry, it's actually like a point on the graph. It's not a hole. You'll see a hole as like an open circle, and then a point is usually like a normal, like closed in dot. So that point that we're given, 2, negative 1/4, you can see that that's the high point of the function that's underneath the like asymptote, which I know it's getting kind of covered up at this point, but that was that orange line that was there. So if that's the high point, that's going to be the maximum for that interval of the range. So instead of going from like negative infinity up to 0, up to the asymptote, we would go from negative infinity up to negative 1/4. So that's that first section, negative infinity up to negative 1/4, and that's basically describing the entire portion that's highlighted in pink now, up until that point. And then remember now, because we're dealing with range, we have to shift our focus to the y coordinates of each point, because range is what possible y values do I have, or like what is the height of the graph. Okay, and then for the next section, we get to shift to like the portion that's above the asymptote. However, like as soon as we're above the asymptote, we're basically at like greater than 0. But after we go above 0, like pretty quickly, there's a hole, because we have a hole at -3 and then 1/21, which I know is a tiny number, but that means that we have to like, there's a gap essentially in the range at at 1/21, because that's the y coordinate of the point. So the next portion of the interval goes from 0, like that's where we're starting, because that's right above the asymptote, and then it stops at 1/21. And I know it feels tiny and it feels like insignificant, but because that hole is there, we have to put it as a part of the range and the domain for that matter. Okay, so from 0 to 1/21, that's a portion of the range. And then after that, we can finally describe like the rest of the range, which is essentially everything above the hole, because there's no other holes on the graph. So everything above the hole would be from 1/21 to infinity. Okay, so if that hole wasn't there, then like after it wouldn't we wouldn't have this here. It would just be from 0 up to infinity. But because the hole was there, we had to stop at the y coordinate of the hole, which is 1 over 21, and then continue again at it and go up to infinity. And then just remember with interval notation, the parentheses means that that number is not included. So like none of these numbers are actually included within the interval. It just means we go up into that point and then we stop. Okay, and then one other thing I want to add, like I said, this extra point was kind of given to us here, like the 2 negative 1/4. If that wasn't given to us, if we didn't know that point, then this would just be negative infinity up to 0, up to the asymptote. It's kind of just like an extra added layer in there that they gave us the maximum point, as opposed to just having us go up to the asymptote. Okay, and then end behavior, rational functions have end behavior as well. It works the same way, however, it is not like the same answers as what we've seen before. That sounds silly to say, but every problem that we've done so far, the sides have like finished up or finished down. So that's why when we fill in end behavior, we've gone to positive or negative infinity. If we look at this rational function graph, one of the sides, or really like both of the sides, so like the far left side and the far right side, those are not going up or down. So we have to consider that. So instead of, for rational functions, instead of going to positive or negative infinity, they're going to be going to an asymptote. So if we look at this graph and we try to use our best judgment about where an asymptote is, and this is where, like, they won't typically be drawn on there for you. You would have to identify where it is. You want to look and see what line are these, like, lines kind of approaching, or what invisible line are these lines approaching? And for this graph, it's y equals 1. And I will tell you right now, that's not super straight. I'll tell you right now, as I was looking through some of these graphs, I was noticing that it wasn't always super clear, because like I said, right here, it kind of looks like, okay, my graph is crossing that line, so how can there be an asymptote there? And that, like, it's just more because it's hard to draw that precise. So if you like think, okay, this is my asymptote, it's horizontal, so it's a y equals, and then it crosses through at 1 on the y-axis, so it's y equals 1, and you're pretty sure that's what it is, but you're not positive, especially if it's a checkpoint or a like test or something like that. Just send me an email and be like, hey, is this the asymptote? And I will confirm it for you, because sometimes it's not super clear. Okay, so this is y equals 1. And then for the first line of end behavior, it's as x approaches negative infinity. So that means the same thing. That's the left. F of x approaches. So on the left side of my graph, it's approaching the asymptote. It's getting infinitely closer to the asymptote, but it's never going to cross it. So that means that it's getting infinitely closer to 1, because the asymptote is 1. And then on the right, that doesn't really look like a 1. On the right side of the graph, or for the second line of end behavior, as x approaches, ooh, that's a typo, sorry. This should be a positive infinity, or you could just not have a sign in front of it. But as x approaches positive infinity, f of x approaches. So this means as the graph goes right, f of x approaches. So if we look at the right side of our graph, I know it looks like it's crossing, but it's approaching the asymptote. It's getting infinitely closer to it, but it's not going to cross that, because that's what an asymptote is. It's like this imaginary boundary line. So that means that f of x approaches 1 as well. So as long as your graph has a horizontal asymptote like that and the tail ends are going to it, that's what your end behavior is approaching, because that's what, like, kind of y value each of your lines are getting closer and closer to. Okay, moving down to this example, we're going to try to find all this stuff for this graph. So find the following key features of the rational function. So vertical asymptote, and there could be more than one. So if you see, like, for example, one part of the graph shoot up and one part of it shoot down, there's vertical asymptote there, so there's one here and here. So we can draw those in. And you can see they kind of like shoot up and around like at x equals -9. So that's where I'm going to draw my line. Sorry, that's kind of crooked. I'll try to fix it. Okay, it's a little bit better. But it's vertical, so it's at x equals, and then it crosses through at x equals -9. I think I might have said +9 accidentally before. So x equals -9 right here. And then the other one is crossing through like about right there at x equals 0, so we can draw that in. And then vertical again, so it's x equals, and then it's crossing through at 0 on the x-axis, so x equals 0. So for vertical asymptotes, it would be x equals -9 and x equals 0. And then for a horizontal asymptote, you can kind of see that like it shoots, the graph shoots like left and right, and it's, ooh, I accidentally erased the vertical one, sorry. The graph shoots like left right here and right over here, and it never really like crosses the x-axis, so that's gonna be where our horizontal asymptote is, so we can draw that in right there. And then for a horizontal asymptote, it's sorry, it's hard to change all fast between the dotted and the regular. Horizontal asymptotes are y equals, and then it crosses through at like y equals 0 at the origin. It's kind of like confusing sometimes because you're like, okay, what's the x-axis? Like, why is the equation y equals? And they're just kind of like reverse like that. Like the equation for a line on the x-axis is y equals 0 because that's all horizontal lines are y equals. And then on the x or on the y-axis, the equation is x equals, and they're just kind of backwards from what you think they would be. Okay, so for the horizontal asymptote, it's y equals 0. And then you can see there's a couple holes on the graph. There's one right here at -4, -1/20. And then there's another one at 6 and then 1/90. Okay, so for the domain, we're just going to start on like the far left side and just go piece by piece. So on the far right, we have this whole section, no holes over there, and then we get to the first asymptote. And that first asymptote is x equals -9. So the whole like kind of left side until we get to x equals -9. So that would be from negative infinity to -9. And then we'll do the little like union symbol. And then the next section would be on the right side of the asymptote until we get to that hole. So from -9 would be our starting point, and then the hole would be our ending point in its domain. So we're focused on the like x coordinate from the hole. So to -4, so that's the x coordinate from the hole, and then the union symbol, and then the next interval would be like starting at the other side of the hole. So from the hole until the next vertical asymptote. So if it's starting, or it's like, yeah, it's like kind of starting part of the interval is the hole. The hole's x coordinate is -4. And then it's up into the next vertical asymptote, so 0, so 4 till 0. And then the union symbol, and we're on the last little section. Oh, no, never mind, there's 2 holes. Okay, sorry, I got a little excited. Okay, so now we have the right side of the asymptote, x equals 0 until we get to that next hole. So from the asymptote x equals 0 until that hole, which is at x equals 6. And then now we're on the last one. So the union symbol, and then start the next interval, which is everything to the right of that hole. So the hole starts at, or the hole is at x equals 6, and then it's going everywhere to the right. So it would be 6 to infinity. Okay, so let me shrink this down so it actually fits in that space. I don't know how this is going to work with the highlighter, but yeah, not great. Okay, so I'm going to go through each little piece and we'll kind of match it up with what it actually looks like on the graph one more time, because I know that these are not the easiest thing in the world. Sorry, it drags the video out a little bit. Okay, so the far left section that was the one that was in pink, so negative infinity up until the first asymptote, -9. That green section on the graph is from the asymptote x equals -9 until the hole at x equals -4. The blue section on the graph is from the hole x equals -4 until the next vertical asymptote x equals 0. The purple section on the graph is from that vertical asymptote x equals 0 until the next hole, which is at x equals 6. And then the last section is from the hole to the right, so that was from x equals 6 to infinity. Okay, so now for the range. So the range gets to be a little bit shorter because we have one less asymptote, but we still have to consider like both holes for the range. So for the, let's see, the bottom, or like the smallest possible values for the range, if our asymptote is at y equals 0, it's difficult to see because they're both so close, but we have one hole that's technically below the asymptote. That's the -4, -1/20th, because the y value is negative. And then one hole that's above the asymptote because the y value is positive. So the like kind of lower portion of our range is from -infinity. And then it wouldn't go up to 0 because we have a hole before we get up to y equals 0. So it would go from -infinity to -1/20th. And then since that's not like a point, it's a hole, we're not saying that's a maximum, so we would have to kind of put the next section that goes from -1/20th up into the asymptote. So the next section, and I can't really even draw this on there because it's so small, would be from -1/20th to 0. So the first section was everything below the hole. The next section, which I can't really draw, is from the hole up into the asymptote 0. And then the next section will be from the asymptote up to the next hole. So we'll do union, and then starting at the asymptote is y equals 0, so we're starting there. And then we're going up to the next hole, which is at y equals 1/9. So from 90th, which is from 0 to 1/90th. And then now we can do everything above that last hole. So everything above that last hole would be beginning at y equals 1/90th and then going up from there. So it'd be union and then 1/90th to infinity because it's everything up from there. Okay, so one kind of like, I guess, trick or like pattern that you could notice when you're writing these is that the ending point of one interval is the beginning of the next one in most cases. So for example, like this one ended at -9, and that's where the next one popped up or started with. This ended at -4, the next one began with -4, and so on. This one ended with the -1/20th, and then this one started with it. Because we're really just describing the entire graph. It's just those very specific points or very specific values that don't work, so we have to like exclude them from saying everything. Okay, and then the end behavior is as x approaches. I know this is going to be another typo because I just copied and pasted it. But the first line is as x approaches negative infinity, so that's the left side of the graph. F of x approaches. So if we look at the far left side of the graph, so like this, I'm gonna go ahead and erase the asymptote. This section right here, you can see that it's getting like that red line is getting infinitely closer to the asymptote, which is at y equals 0. Remember, y and f of x are the same. So that means that f of x approaches 0. Because that's the line that it's going to like get really, really close to, but never cross or touch. So that's what it's approaching. It's approaching 0. And you wouldn't have to like say y equals 0 or anything like that because f of x and y they mean the same thing. And then the second line is x approaches infinity, so that's the right side of the graph. So if we look at the right side of the graph over here, you can see it's approaching that same line. It's approaching y equals 0. It's never going to cross it or anything like that. So f of x approaches 0. Okay, so I don't want to say always because I'm not sure if there's ever like a counterexample, but most of the examples that I can think of right now, when you're writing end behavior, they're going to be approaching the same exact like asymptote. So they should be approaching the same number. Might be a good way to kind of like check your work. So 22.2 is holes and asymptotes from rules of rational functions. So this section goes into more about like what causes these asymptotes and holes. So the parent function for rational is f of x equals 1 over x. The asymptotes come from basically what values are impossible to get from the function or what values make the function undefined. So if we look at the parent function 1 over x, if I put a 0 in for x, then I have a 0 in the denominator. And you can't have a 0 in the denominator, it makes the function undefined. So what I just did is I put 0 in for x, so things like x equals 0. Well, that's a vertical line. If I draw that vertical line on the graph of the parent function, that pretty much looks like the asymptote. So that's where the vertical asymptote comes from, is from whatever makes the function undefined, whatever makes the denominator equal 0. So for a vertical asymptote, at least for the parent function, it's x equals 0 because it makes the function undefined. It can change depending on if you have other values in the denominator though. And then for the horizontal asymptote, so horizontal asymptotes, they are like horizontal lines, which are y equals 0. So they have to do with like the possible y values. So there's kind of like this impossible y value to get from a rational function, which if my parent function is 1 over x, think about what happens if we put in like a really big number for x. Well, that'd be 1 over 200. And if we put a really small number in for x, that'd be like 1 over 0.001 or something. But neither of those are going to end up being 0. Like I can keep putting bigger and bigger numbers in, or keep putting smaller and smaller numbers in for x. There's no x value that I can substitute in here that will get me an output value of 0. Like that's impossible to get, is to make 1 over a number equal 0. It's not possible. So the impossible number to get is that y equals 0, and that's going to be our horizontal asymptote, and you can see it on the graph. So for the horizontal asymptote, it's y equals 0 because it's impossible to get from this function. We can't make 1 over x, 1 over any number actually equal 0. Okay, so that's just for the parent function in general. That's kind of where they start. And then there's some different like kind of like rules that we can use in order to find the asymptotes of like more complex functions. Okay, so this table is super, super important. If you can't print it, definitely write it. If for whatever reason you can't write it, definitely take a picture of it and like save it to favorites or something. So there's 3 different types of interruptions. There's vertical asymptote, horizontal, and holes. So the first one, the vertical asymptote, I'm pretty much going to read this verbatim. So for the vertical asymptote, If there's a polynomial factor in the denominator that does not occur in the numerator, there will be a vertical asymptote at the x value that makes the factor equal 0. So our example over here on the right is f of x equals 5 over x plus 1. So there is a factor, or there is a polynomial factor in the denominator. It's x plus 1. So there's that. So if there is 1 in the denominator, yep, we check that box. And then the second one is that it does not occur in the numerator. So that x plus 1 is not also in the numerator. So we check that box also. Then there will be a vertical asymptote that makes at the x value that makes the factor equal 0. So we're like, okay, what x value would make x plus 1 equal 0? Well, it would be x equals negative 1. But if you ever have like a more complex factor where like you're not really sure like in your head what it is, just take whatever is in the denominator and set the denominator equal to 0. And then solve for x. So for example, we do x plus 1, set that equal to 0, and then solve for x. So I would subtract 1 over, and then I would get x equals negative 1, and then that is my vertical asymptote. And we're at the point now I'm going to start shortening vertical asymptote to just VA. So vertical asymptote is x equals negative 1. Okay, so vertical asymptote is just whatever makes the denominator equal 0. In this case, if I were to put a negative 1 in for x, it'd be negative 1 plus 1 is 0. Okay, and then moving down to horizontal asymptote. So for horizontal asymptote, if there's kind of two cases. So if the degree is higher in the denominator, the horizontal asymptote occurs at y equals 0. So I'm going to kind of separate this into two sections because it kind of is two different sections. So there's like case 1 and case 2. So the first case, if the degree is higher in the denominator, the horizontal asymptote occurs at 0. So it's referring to like the power over x. So this is a degree 2, and this would be a degree 1. So it checks that box. The degree is higher in the denominator. So then we have a horizontal asymptote at y equals 0. So we can say there's a horizontal asymptote at y equals 0. Okay, so we're like 2 rules in, and I could already tell like this would be kind of hard to like memorize and remember the difference between these all. So that's why it's important to like save this and make sure you have it to reference later on. Okay, so the second case for a horizontal asymptote. So if the degree is the same in the numerator and the denominator, the horizontal asymptote equals the quotient of the leading coefficients. So horizontal asymptote is the quotient of the lead coefficients. So we got to check the first box is that the degrees are the same. So this is a degree 1, this is degree 1, so they have the same degree in the numerator and denominator. If that's the case, then the horizontal asymptote is the quotient of the leading coefficients. So like if we look at the leading coefficients, 1 is a 2 and 1 is a 5, and we just keep those in that same exact order. So the horizontal asymptote would be the lead coefficient from the numerator, 2, over the lead coefficient from the denominator, 5. So y equals 2/5. Okay, so kind of like, I keep calling them cases, but they kind of are. Case 1 is just where the degree is higher in the denominator. If so, it's just automatically y equals 0. If they're the same in the numerator, if they're the same in the numerator and denominator, then the horizontal asymptote is the quotient of the lead coefficients. Okay, and then last little part. So for holes occur when the numerator and denominator share a common factor that does not occur more in the denominator. So if we look at our function, there's an x plus 5 in the numerator and an x plus 5 in the denominator. So they share a common factor. And then the part that says that does not occur more in the denominator is referring to like exponents over the factors. So like if this was an x plus 5 squared, that would kind of break that kind of like rule that says that does not occur more in the denominator because there's a higher power in the denominator. But in this case, they're both the first power, like they're both just x plus 5. They're not being squared, cubed, or anything like that. So it does not occur more in the denominator, so that means there's going to be a whole there. And then the next part, the whole occurs at the x value that makes the common factor equal 0. So the common factor is x plus 5. If you're not sure what x value makes that equal 0, you can take that common factor and just set it equal to 0 and then solve for x. I know with x plus 5, it's a little bit like straightforward to find in your head, but this is just kind of like how you could do it if it was more difficult to figure it out in your head. But for x plus 5 equals 0, if I wanted to solve for x, I would subtract over the 5, and then I would get x equals negative 5. So I have a whole at x equals negative 5, because that's the x value that makes the common factor equal 0, because negative 5 plus 5 would equal 0. And then if you have to find the whole, then you have to take that x value and actually substitute it into the function. So if we take that x equals negative 5, substitute it into the function, it would be f of negative 5 and then this part's kind of funky, so we're going to do a couple like examples of it. So it'll be negative 5 and for x plus 5. I'm not going to put that part that's that like numerator factor in parentheses. And then, so we're taking the negative 5, putting it in for the x's, so right here, right here, and right here. So then in the denominator, it's negative 5 plus 5 times negative 5 plus 2. So right here, and then we'll simplify each part. So in the numerator, that's 0. In the denominator, negative 5 plus 5 is 0 in the first set of parentheses. And then over there, negative 5 plus 2 is negative 3 in the second parentheses. So yes, technically this does simplify to 0. But so it does simplify to 0, and you can't technically have a 0 in the denominator, so that's why there's a whole here. But we still need to kind of write all this part out in order to actually find the y value of a whole, because the function is not actually defined there. So it's kind of okay that it's not defined as we're simplifying this. This is just the process we have to go through to find the y value of the whole. So think of this, since there's no other factors in the numerator, think of this as like times 1. And then anything divided by itself cancels out. So I can think of this as like 0 times, I'm going to make this into two fractions, 0 over 0, and then times 1 over negative 3. And again, it is undefined, but the function's undefined there. That's kind of besides the point. 0 over 0, anything divided by itself cancels out or like is 1. So we can think of that as canceling out and just leaving us with negative 1/3. So we put in negative 5 and we got out a negative 1/3. So that would be like the y value for the whole. So we would have a whole for this function at the point at negative 5 for x and then at negative 1/3 for y. So negative 5, negative 1/3. We will do another example of that though, so don't worry, because that is like kind of weird with the like undefined but not part. Okay, so this is the last example. Sorry, this section is like pretty heavy. But find the interruptions in f of x equals x minus 4 times x plus 1 over x plus 1 times x squared minus 9x plus 20. So in order to be able to make sure we find all the interruptions, we have to make sure that everything is factored completely. So the x squared minus 9x plus 20, that part can be factored. A is 1, so I would just need numbers that multiply to c and add up to b. So I would need to find a pair of numbers that multiply to 20 and add up to -9. So multiplies to 20 and adds up to -9. That pair of numbers would be -4 and -5, because -4 times -5 would be a +20, and then -4 plus 5 would be a -9. So that means that x squared minus 9x plus 20 factors into x minus 4 times x minus 5. So now we don't really need this part anymore, so I'm just going to rewrite the function without it, but with the like x minus 4 and x minus 5 replacing it. So f of x is equal to x minus 4 times x plus 1, and then in the denominator x plus 1 times x minus 4 times x minus 5. Okay, and then we're just going to go piece by piece. So like we'll start with the vertical asymptote all the way at the top. So for vertical asymptote, if there's a polynomial factor in the denominator that does not occur in the numerator, there's going to be a vertical asymptote. So we do have that. We have the factor x minus 5 that is in the denominator but not in the numerator. So that's why we have to factor the problem that it's not already fully factored, like we did here with the x squared minus 9x plus 20. So that factor x minus 9 is in the denominator, not in the numerator, so that's going to result in a vertical asymptote. So the vertical asymptote is x equals whatever makes that factor equal 0. So the x value that I would have to plug in would be 5, because 5 minus 5 is 0. So we'd have a vertical asymptote at x equals 5. And then we can move down to the horizontal asymptote. So the first case, if the degree is higher in the denominator, the horizontal asymptote is y equals 0. Okay, so these are in factored form. Well, kind of. Yeah, now that we've factored them, they're in factored form. You could use the original problem for this too as well. But if we look at the numerator, this is 2 x's being multiplied together, so it would be a degree 2. You just have to count how many x's are being multiplied together when it's in factored form. And then in the denominator, this is 3 x's being multiplied together. So in the denominator, that would be degree 3. So that means that we fall under that like first category of horizontal asymptote. If the degree is higher in the denominator, the horizontal asymptote occurs at y equals 0. And our denominator has a degree 3, our numerator only has a degree 2. So that means that, yes, like our degree is higher in the denominator, so our horizontal asymptote would be at y equals 0. And then the last part is finding the holes. So for holes occur when the numerator and denominator share a common factor that does not occur more in the denominator. So that happens in 2 cases here. So they share a x minus 4 and they share an x plus 1. So we're going to have 2 holes on this graph. So the first one, not necessarily the first one, but the first one we'll do together. So it says the hole occurs at the x value that makes the common factor equal 0. So if one common factor is x minus 4, you can either set that equal to 0 to find it, or if you're like, okay, a 4 would make this equal 0, that's where the hole is. So x equals 4, and then we have to find the y value that goes along with it. So in order to I'm gonna erase some of this. I don't really like the way I wrote it, but the x value that would make this factor equal 0 would have to be an x equals 4, so there's a hole there. So we'll do x equals 4, and then we have to find the entire point where the hole is. So we would find f of 4. So we would take 4 and we would substitute it into the function for x. So it would be like 4 minus 4. I'm going to just go ahead and rewrite the function over here really quick, actually, and then I'll just sub in the 4 for it. So the function originally was f of x equals x minus 4 times x plus 1, and then times, or over, x plus 1 times x minus 4 times x minus 5. And then if we're finding x equals 4, I have to take that 4 and put it in for all of my x's, every single one. So I'm just going to, instead of rewriting it, I'll just put the 4 in for each of those spots. So f of 4, I'll put a 4 right here, right here, right here, right here, and right here. And then we'll simplify. So then this is, in the numerator, 4 minus 4 is 0, times 4 plus 1 is 5. In the denominator, 4 plus 1 is 5, and then in the denominator, 4 minus 4 times 0, and then 4 minus 5 is negative 1, so times negative 1. Okay, I'm going to rearrange this a bit and put the 0 over the 0, so we're kind of pairing up these two. And then remember, in a normal case, like 0 in the denominator, if it's a factor, it would make the whole thing undefined. But in this case, like we know the function is undefined there. It's a hole, like that's what a hole is. This is just the process we have to follow to find the y coordinate of the hole. So in the numerator, I still have this 5. And then in the denominator, I have 5 times negative 1, so I'll just make that negative 5. And then think of 0 over 0 as anything divided by itself cancels out or is 1. And then 5 over negative 5, or 5 divided by negative 5, is negative 1. So that output value is our y coordinate for the hole. So we put in x equals 4. We knew there was a hole there. We got out negative 1. So there's a hole at the point 4, negative 1. It's one hole. And then we still have to do that same process for the other hole. So remember, the holes come from like the shared factors, 1 in the numerator, 1 in the denominator. So there was one with the x minus 4s. There's also one with the x plus 1s, because there's one of those in the numerator and denominator. So the x value that would make x plus 1 equal 0 would be negative 1. And if it's easier, you can think of like what makes the denominator 0, because sometimes that's easier to connect with, like, oh, that's undefined or there's a hole, but they're the same factors, so it doesn't matter which one you look at. So then at x equals negative 1, we have a hole. So that means that we would find f of negative 1. I'm just going to copy down the function first, and then I'll replace all the x's with negative 1s. So x minus 4 times x plus 1, and then over x plus 1 times x minus 4 times x minus 5, and then we'll take that negative 1 and put it in for all of the x's. So it'll go here, 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 and here. So negative 1, negative 1, negative 1, negative 1, and negative 1, and then we'll simplify. Sorry, sometimes my hand hits the like back button. Okay, so negative 1 minus 4 is negative 5. Negative 1 plus negative 1 is 0. I'm going to keep this in the same structure as the first one. You can use parentheses or like the dot for multiplication. It doesn't really matter here, whatever you're comfortable with. And then in the denominator, negative 1 plus 1 is 0, and then times negative 4 minus or sorry, I keep saying negative 4 first, but negative 1 minus 4, negative 5. And then right here, negative 1 minus 5 is negative 6. And then if you want, you can just kind of look at what common factors like cancel each other out if you feel comfortable with it. I'm going to try to keep it in the same structure as we did the first part. So we'll do 0 over 0, and then times, sorry, it's like really bad today. And then left over in the numerator, I have the negative 5. And then in the denominator, I have negative 5 times negative 6. I'm going to go ahead and just leave those separate. You'll see why in a second. And then the zeros became their own fractions. We'll do 0 over 0 cancels out. That's just 1. And then on the other fraction, negative 5 divided by negative 5, those can cancel out. So if everything cancels out in the numerator, I just have a 1. So this would result in a negative 1/6. So I put in x equals negative 1, and I got out negative 1/6. So that's my second whole. Okay, so whole at negative 1, negative 6. I'm just going to write that up with my like asymptotes and stuff like that. So for our wholes, we had the first one we found was at 4, negative 1. The second one we found was at negative 1, negative 1/6. And then our vertical asymptote was at x equals 5, horizontal is at y equals 0, and then we got our holes there. Okay, so I know there's a lot. I'm sorry, I like try to cut a section out, but like biggest thing is like this. You need this table. It would be super difficult to try to remember all those different distinctions like without it. So make sure you have it somewhere where you can easily access it, and kind of go back and find it.